to talk about exponential functions, what I want to do is, create one real quick. Okay. So we are going to operate for this next thing in a very, very non-realistic setting that these mice, this population of mice is going to continue to grow without any sort of upper limit. Obviously, that's not really true. Cool? All right. So I start out with 6 mice. So at 0 months, how many mice do I have? 6. Now, the population of mice is going to double every month. So after 1 month,
12.
Can you guys fill out this table?
Would it be 18?
It would not.
Would it be 24?
It would be 24 because it doubled again, right?
I see. Very cool.
This is a lot of mice.
Why do I feel like you could do this mentally?
Because I'm doing it mentally right now.
I did it mentally until 192.
Same. Yeah, probably.
And then I just. No, I didn't. But I'm saying I got up to.
Unfair.
It could be better.
That's like saying it's unfair for like
A race car driver.
to drive fast, or unfair for Usain Bolt to run fast. Like he worked his rear end off, like training to do that, right? And I'd like to point out what I do all day, every day. Of course, I can multiply by 2 in my head. I do math all day. I strengthen my math muscles in my brain all day, every day. Yeah, that's right. I said it. My math muscles. It's crazy, right?
I thought you would do like English.
Nah, you should see me read a book. It goes poorly.
You don't ever read?
I do read. And by read, I mean listen to books on tape while I walk the dogs. But my eye muscles are not trained to like sit and read a book. Like my eyes get tired really fast. But I love listening to stories. Because you want to know why? These muscles, not so much trained like my math muscles.
Good spiel.
Okay, so now, guys, what if I said 18 months?
Miss Weister?
Wouldn't it be great if we could come up with a shortcut to help us figure this out? Is this okay?
Yes.
I think we did this last year.
We did. We did. Now, some of this is going to be familiar from last year. Some of the other stuff we're going to do later on is not going to be familiar from last year. Yes.
Would you do 6 to the power of 18?
I would not do 6 to the 18th power. But I like where you're starting to think. So, hey guys, how did we get this 12?
Multiply by 2.
6 times 2. How did we get the 24?
12 times.
We did 12, but that 12 was 6 times 2. And what did we do to that 12? We times 2 again.
Oh, so we're just gonna do
And then to get to the 48, we did that 12, or that 24, and then we multiplied by 2 again. So in reality, we had 6 times 2, 6 times 2 squared, 6 times 2 to the third. Is everybody with me?
So can we do 6 times 2 for the 18?
Well, so we're not going to worry about the 18th yet. What if I just came up with what is the equation that is our shortcut? You guys, if I say 6 times 2 to the months equals the mice, would that kind of make some sense to us if we put it all in context like this? And then we can say, well, wait a minute. Now, if I want to know how many mice will there be in 18 months,
You could plug in the months.
now we have an equation into which we can plug in our months. And no, I do not know the answer of 6 times 2 to the 18th. I'm good. I am not that good. Let's see. Do you guys think I could try to figure this out?
Yeah.
Okay, so that would become 2 to the 6th times 2 to the 6th times 2 to the 6th, which is 64 times 64 times 64, which is 8 times 8 times 8 times 8 times 8 times 8. So 8 to the 3rd, 8 to the 6th,
You got this, Miss Meister.
which I'm going to call guys, I don't want to do this by hand. What are we getting, y'all?
1,572,000.
1,572,000. 864 mice.
It's a lot.
It,
No.
it is unlikely that it actually gets that high, right? It said, that's why I said unlikely, not. I do know that it is not likely. I do know that it is unlikely.
In a lab, though.
In a lab where people work, probably not. 1 million mice is a lot of mice. Yeah?
I think it's possible.
All right, now, what if I ask you, how long will it take so that I have 196,608 mice? We would end up kind of doing this. 196,608 has to equal 6 times 2 to the m power. I don't know how to solve that. Do you guys know how to solve that? Well, the first thing I might do is divide by 6, just to try to make these numbers smaller. And let's see, that's 3, 8, 1, 0, 2. Is that right? 3, 2, 7, 6, 8. I don't know what was going on inside my head. 3, 2, 7, 6, 8 equals 2 to some power that I'm going to say m for months. And from here, we have lots of options. For right now, you know what I would do?
Square root.
We can't take the square root. We kind of have to take the mth root, right? We would want to take the mth root to get rid of that m, and that's not really a thing. For right now, you know what I would do?
Leave it.
Guess and check.
I like that method.
Do some guess and check real quick. Just do 2 to a few different exponents. Hey guys, guess what I know the answer is bigger than? 9. Because 9 was 3,072 mice, right? And guess what I know it's less than?
18.
So when you do your guess and check, pick something between 9 and 18. 15? What is 2 to the 15th?
32,000.
Oh, so m equals 15 months. Now, I can show you the algebraic way to solve this. In fact, I will later on this week. Probably on Friday. We good?
When I enter 15 into the equation of 6 times 2, that it doesn't equal 3276.
What does it equal? Oh, it's not supposed to. It should equal 196,608. Is that what it equals?
Yeah. Oh, wait. Yeah.
So that 32,000 is like dividing through by that initial 6.
Gotcha.
Everybody good? Okay. So This is an example of an exponential function, and all exponential functions are of the form a times b to the x power. How are we feeling so far? Bless you. So this was 6 times 2 to the x power, yeah?
Yes.
So why 6?
That's the starting.
So a is always your initial value. And b is always what we're gonna call it either a growth or decay factor. And it turns out that if you, like, how do I make a number get smaller? By multiplying, because, right, what I do is I multiply by b over and over and over again. You multiply by a number smaller than 1. So if b is a smaller than 1, we have what we call a decay or a depreciation model. But if b is bigger than 1, like, I don't know, 2, it causes things to go up. We call it a growth model or an appreciation model. And when things grow or decay exponentially, okay, exponential growth is whoosh. It starts out growing really slow but grows really fast. If you look at how the number of mice changed over time, it started going. First, we jumped by 6 mice, then by 12 mice. Like, the number of mice jumped very, very quickly, okay? Things that grow exponentially very frequently include populations of lots of different kinds, investment accounts, hopefully. We're going to spend a little bit of time talking about those. Depreciation, things that decay. If I had an ice cube, and I sat it on this table and just left it go, what's going to happen to the ice cube?
It will melt.
It will melt. Everybody good? Or if I have, I don't know, a radioactive isotope, such as carbon-14, which is used to find dates of really, really old things because it decays very, very consistently. Or the value of your car after you buy it. Is everybody good? All right, so we're going to learn the math behind those things. In fact, you would say this whole unit is about exponential functions or logarithmic functions, which are very much related. Okay, so here we go. So somebody bought a new car for $16,799.
How's the steal?
Depends on the car.
Well, it says new.
Could be a Kia.
New's
Kia
new.
Soul.
It would probably not a Kia Soul, but like a Kia.
Kia Soul.
What's Kia's, like a Kia Rio?
Those tiny,
Like the little tiny, yeah.
just metal.
So what's the initial value of this car?
$16,799.
All right, now, the next thing we want to do is talk about the decay factor. Like, what are we going to multiply by? Now, if it is going down in value, what do we know about that value? It has to be less than 1. And it is, in fact, less than 1. But it is not.
0.15?
It is not 0.15.
Would it be 0.85?
It would be 0.85. Each year, the car has 100% of the balance at the beginning of the year. And if it's losing 15% of its value, how much is it gaining? Or how much is it retaining? 85%. So my decay factor in this case, which I'm going to label as B, since we did like the initial value is A and the decay factor is B, is going to be 0.85. We're going to write that 85% in context. All right. So if I ask you guys, what is a function that models the value of the car. So I'm choosing to write this function as v of y. Why do you guys think I chose those two variables?
Value in year.
Value and years are my two variables here. Okay, so my initial value is going to be 16,799 times my factor to the y power. So if I want to know how much is the car going to be worth in 5 years, I want to find v of 5.
Would we
What are we finding?
It's value in 5 years.
Huh? I copied Savina, is that right?
$7,453.
And 89 cents.
Yes.
So why would somebody buy a car? In 5 years, it's not worth half as much.
It's still.
to get you places?
The value isn't just its monetary value, right? Its function also has value to it. Not like function like f of x or v of y. Okay? But it's the same thing like, why would you buy a house? Because you have to pay so much interest when you pay off a loan, right? When you borrow money, you pay interest. Well, you're putting that money to use in one way or the other. Yeah.
Isn't it like when you buy a car, like as soon as you drive off the lot, it goes down like 15% or something insane?
Yes, no, yes. In the sense that usually there's like it's not as soon. In that there's usually there's some rules that car manufacturers have to follow. If let's say you own a car for a year and it has 3 or 4 different problems,
Yeah.
they call it a lemon because it leaves a sour taste in your mouth. And there are lemon laws about the values of a car and whether or not you have to keep that car or whatever. Does that make sense?
Yeah.
And certainly right away, no. And it also depends on the current economy. So if you guys, I don't know how much you guys followed what was going on post-COVID with, they called it, there was a chip shortage, right? So most cars nowadays have computers in them. And so if something goes wrong with the computer, or if they don't have enough computer chips to run the car, then, they can't build the cars. And so what happened is there was a huge shortage of cars, and it wasn't the cars themselves, but the computer chips. And so right now, my car that I'm currently driving is worth exactly what I paid for it because there's no new cars on the market. Relatively new used cars are very, very valuable right now. Does that make sense? So there is some ebb and flow, and supply and demand is a big component of this idea. Okay. Why don't you guys give this one a shot?
Maddie, you should be close to finishing up with the previous one.
What do I know about B? If it's a growth factor, it's going up. It has to be greater than 1. So we're still going to start with our 100%, but instead of subtracting 6%, we're going to add it. If you put T or X, it's fine. Everybody good? And then how many in 5 years? We'll do 810,000 times 1.06 to the 5th power. Yep. 83,963.
Well, if you round it up.
Does it round up?
Yeah.
Yeah. Certainly, let's not put down like half a person. I don't think those people exist. Now, what you would want to be really, really careful of is order of operations. Which one? So, like, what you wouldn't want to do, and I'm only pointing this out because kids in the past have done it. They do the 810,000 times 1.06, and then take that answer to the 5th power. My guess is your calculator gives you something that is very, very much not a number. It might even say overflow error if you try to do that, okay? So order of operations says you do the 1.06 to the 5th power first.
Miss Meister,
Yes,
if we just enter it into our calculator like that, will
Well,
give us the correct
it
answer?
will give you the correct answer. Indeed. Indeed it will. How are we feeling about exponential expressions so far?
I feel like you always ask that question when it's about to get worse.
No, I'm done for today.
Uh,
I think, right? I have